Hi everyone, we are Johannes Fichte,
Markus Hecher,
Ciaran McCreesh,
Shahab.
and this is a talk about some of the things that can go wrong when you try to run computational experiments on modern hardware. Now that multi-core hardware is standard, we often run more than one experiment at the same time on the same machine. But just how much of an effect does running, say, 8 experiments at the same time on an 8-core machine actually have on performance? Some research groups have access to carefully calibrated server hardware for running experiments, whilst others just use standard desktop or laptop machines. Does this make any particular difference to experimental runtimes, or is this simply a matter of being able to run larger experiments if you have access to better hardware? And how stable is hardware over time? If we run one set of experiments on one day, and a second set the next day, when the weather is different, or after having rebooted a machine, might this have a material effect on runtimes which could lead us to the wrong conclusions? In constraint programming, we often rely upon empirical evaluations to determine whether a new algorithm or solving technique is any good. And if a new solver runs 10 times faster than the previous state-of-the-art, then that's fairly easy to demonstrate. But what if we're looking to do something more subtle? For example, if we are looking to determine the effect of a small change to a solver's source code, we might be looking at a performance difference of only a few percent. And this can be something that's very hard to measure reliably. In other empirical sciences, a lot of thought is put into experimental methodology to eliminate external sources of variability and to allow for reproducibility. And we think this is something that needs to be thought about more in this area as well. Public challenges and solver competitions now deal quite well with replicability by using well-defined platforms and having a specified set of benchmark instances. But things get far less clear when we're looking at non-competitive evaluations and trying to go beyond determining which solver is the best. And most people know that modern hardware can sometimes be a bit weird and a bit badly behaved. But a lot of people underestimate just how big the problem is. That there is a general assumption that hardware is deterministic, so if you run the same experiment with the same solver on the same hardware, then, for example, runtime is something that you can just measure. In this talk we're going to go into a bit more detail and show that this really isn't the case, that, for example, runtime is not something that you can just treat as a deterministic measurement. This talk doesn't go into great detail on, for example, experimental protocols or failure analysis or software considerations. We're really just looking at a few aspects of modern hardware and the effect this has on experiments. But we're hoping that this will encourage discussion and a lot more focus on experimental methodology going forward. Our contributions in this paper are to revisit the approach we take to empirical experiments for combinatorial solvers, and to illustrate some of the aspects of uncertainty that arise in modern hardware. We give an overview of some standard measures, their effects and potential errors, and some biased suggestions for useful tools when running experiments. We also look at the feasibility of carrying out experiments when you only have limited access to hardware. In particular, we're not saying that everybody needs to run perfect experiments all the time. What we're saying is, if you're in a situation where you don't have access to a carefully calibrated experimental setup, then you should be aware of how large the errors can be and how this limits what type of experiments you can carry out. And in the paper, but not in this talk, we also give an overview and comparison of some of the tools that people use to run computational experiments.
But what's in our box then? Before we start, let's go a step back and fix basic notations as you would do in a proper theoretical talk. The cat in the room are 3 terms: repeatability, replicability, and reproducibility. Repeatability addresses the topic of repeating a computation by the very same researcher with the same equipment with the outcome that the same result is obtained with high confidence. Repeatability aims to estimate random errors inherent in any observations. So when we talk about combinatorial solvers, we can say that we run the same solver multiple times with the exact same configuration on the same or different hardware. Related works are toolings like runsolver or benchexec. Replicability goes beyond. It asks for replicating a computation by independent researchers with access to the original artifacts and same methodology. Support by original authors is clearly allowed. Outcome should be that the new group reliably reaches the same result. Replicability aims to copy or reassemble the suggested method or approach, which sometimes in computational sciences is also called recomputability. So when talking about combinatorial solvers, we can say that we run the same solver and configuration by independent researchers on different systems and on different instances. Related works are various and include software heritage projects, recomputation manifestos, or standardized Linux environments. Now, by the term reproducibility, we mean that the computation can be reproduced with the same outcome, but maybe varying details, including minor modifications to the methods or alternative methods. This usually includes that independent researchers develop their own artifacts without detailed help of the original authors. Here we aim to achieve similar conclusions, ideally with varying input. For combinatorial solvers, we can see this as another group constructs an alternative solver implementing similar algorithmic ideas and use other benchmark instances. Works into these directions are by Don Knud's set solvers and various algorithm engineering works. So in short, our primary focus here is repeatability. So what's the usual scientific approach to run an empirical evaluation? Well, it takes time, and seniors don't have that much time. So pick a master or PhD student, assume that he knows what she or he is doing. Well, they are good with technology, right? Let them run the evaluation. As system, we take whatever is at hand and doesn't produce too much work. This might be a standalone computer, such as a desktop or mobile computer. If we are on the clock or have large experiments and university has access to a large cluster, take the cluster and somehow try to get things running there, which usually is anyways a bit of a pain because those systems are really complicated. Common measurements in the community are runtime and memory consumption, which both are often also used for resource limitations. Additionally, we're interested in the number of solved instances within a limited time slot. A commonly used assumption by theorists and also many practitioners is that modern hardware is similar to a simplified machine model, meaning we are running on the von Neumann architecture and everything is deterministic. Sorry to disappoint you. This is not always true. In fact, there has been a huge but somewhat salient change in computer architecture around 2006 when multi-core processors were widely introduced and progress in faster silicon slowed down significantly. Multi-core processors and modern operating systems introduced automatic parallel execution. In addition, modern processors can dynamically boost the frequency depending on load for economic reasons and battery lifetime, as well as for physical reasons, as high clock speeds cannot be maintained over a long period of time without destroying the silicon. So clearly this leads to unpredictable behavior without additional considerations. The question, can it significantly interfere with experiments? Since modern CPUs vary the clock speed between 0.8 GHz and 5+ GHz, a factor of 5 can easily be seen in theory. Additionally, slower clock speeds affect the memory pipeline, and theoretically we might even see much higher differences. You will see in a bit that this is also the case in practice. What are consequences when evaluating implementations? We believe that it requires a more rigorous process, understanding of measurements, and effects of potential errors. So we need to clearly state that some widely believed assumptions from the 90s and 2000s are simply not valid anymore.
We designed a simple experiment to illustrate problems around uncertainty on modern hardware. Take a state-of-the-art SAT solver, 200 instances, and run the solver in different platforms. So server CPU, workstation CPU, and mobile CPU. The experiment aims at demonstrating problems in parallel execution, automatic or manual frequency scaling, and thermal issues in particular of mobile devices. Our experiment, we took a server CPU, a workstation CPU, which can also be found in compact servers, an expensive high-performance server CPU, and a mobile CPU, which can also be found in systems such as small form factor, bare-bone hardware, running on multiple instances in parallel. That the CPUs allow for different maximum frequency scaling, where in fact the desktop CPU can scale the highest. Now the column S15 states the total number of solved instances within 15 minutes. And TFH refers to the total runtime of the solved instances. In terms of number of solved instances, we can see that for a stable benchmark set, there is only a small difference. However, parallel execution can be problematic on mobile processors if we run many instances of the solver in parallel. The 8% difference in terms of solved instances can still be neglected. Almost doubling the total runtime can in fact be problematic, especially when we try to evaluate someone else's solver quick and employ available parallelity. But run our own solver many times and at some point see an improvement. This might be in some cases not even be related to an engineering optimization in the code, but rather the origin of low degree of occupation on the hardware. The mobile CPU, we went into more detail. The table here illustrates the number of parallel running solver instances, together with the number of solved instances within 1 minute, 10 minutes, 15 minutes, and 25 minutes. In addition, we state the total runtime for obtaining the solved instances. Note that this differs from the runtime of the experiment. While it might seem in the following that one should never use parallel execution on a system, for economic reasons one should instead balance effectiveness. Finally, we list the number of solved instances within 5,000 seconds, which recently got common as measure in SAT competitions. We easily observe that timeouts can have a reasonable large influence on your benchmark set. in particular when one is considering a benchmark set that was designed to facilitate increasing hardness behavior. Runtime-based measures might even be less stable here than hoped, and we can see a difference of more than 20% in a bad setup. Clearly, parallel executions influence the runtime and number of solved instances. A standard approach to avoid such problems is simply to test for stability of the used system by running multiple experiments. Here we don't just want to state the obvious, but also tell you why this is the case. In fact, when monitoring CPU frequency, maximum core temperature, and average core temperature, we can see that running too many parallel solver instances results in a higher average temperature and higher maximum temperature. In consequence, the CPU needs to scale down to cool down and can only run at smaller clock speed on average. As we can see from the total runtime of the experiment, it does pay off to run multiple instances in parallel. In the paper, we provide insights beyond these two simple experiments. We state potential origins and where to find details in system documentations, which might be a good starting point for additional future investigations. Provide an extensive overview on standard measures, runtime, CPU scaling, memory consumption, and parallel execution. We explain expected errors, toolings to measure resources and potential pitfalls, as well as toolings to enforce runtime restrictions, which can be far more complex than expected. We briefly survey available literature, which hopefully serves as entry point to young researchers in the future. Most importantly, we describe reasons when to use certain tools or not to use these tools under pragmatic considerations. Simply, sometimes we need to follow what our system provides and whether we have strong restrictions on permissions at the system. Then we need to balance between best way to obtain the data and what is possible on the system. Take a look into our paper and let's start an actual community discussion. In summary, you have seen situations where we can observe complications with modern CPUs. Take-home message, we'd like you to keep the following points in mind. Don't just build simple, but also try to keep experiments simple and reconstructible. Know your system and avoid overhead. Measuring, keep external influence as low as possible. There might be unexpected things happening. Avoid measures that are easily affected by hardware dependencies. Make your evaluations available and expect varying behavior on other systems. Something that's very generic and could also be told in an Experimental Physics 101 lecture. Name advantages and disadvantages of your approach. Properly state hypotheses, preconditions, and instances for the experiment. Name your choices. You need empirical evaluations, but since runtime or number of solved instances may depend on your hardware and setup, be thorough, cautious, and keep in mind that old assumptions might not hold anymore. We believe that our work opens a variety of topics and discussions. A totally unclear point might be at this moment, what's the effect of branch prediction? Then can we have proper how-tos for young researchers? Could standardized benchmark protocols help to focus on research for both sides, the carrying out researcher, as well as the reader? So far we have not discussed cluster schedulers, which can however become inherently complicated and might show issues that are fairly complex to grasp. We think that a common user configuration for these systems could be helpful, also for researchers when addressing administrators of clusters. Finally, let's all start a discussion on those topics. Thanks for watching and hope to see you soon online.